Let's say you want to give your favorite math professor a lot of jelly beans, but all you have for packing materials is a 6 by 14 inch piece of cardboard. You can't just lay them on top, that doesn't work at all. So how do you turn that piece of cardboard into a box? Well, you can cut off 4 equally sized square corners and fold up the edges and, well, that works. But let's look at all the different boxes you can make depending on how big the cut out squares really are. They don't all have to have the same volume, right? So how do you figure out how much to cut out to make the box with the largest possible volume so you can pack in the most jelly beans? Good thing you're learning calculus because this is an optimization problem. Optimization problems are all about finding the largest or smallest quantity given some constraints. In our situation, we want to figure out how big a cutout to make to maximize the volume, and the volume of a box is length times width times height. But that's too many variables. Can we express the volume as a function of a single variable? Well, we're trying to find out how big of a cutout to make so that we maximize the volume, so let's use x for the length of the cutout. Now, if x is the length of the side cut out, L equals 14 minus 2x because 2 sides have been cut out. W equals 6 minus 2x, and height, as we know, is x. So, now we have the volume expressed as a function of x, which we can multiply out. Where the derivative equals 0, maximum and minimum values exist, since the slope of the tangent line at those points are 0. No problem, taking a derivative here is a piece of cake. Using the quadratic formula, you solve when you set the derivative of the volume equal to 0. Setting the derivative equal to 0 and solving, we find 2 possible values of x. But we can cut out 2 corners bigger than half the length of the shorter side of the cardboard, so we'll ignore the solution that is larger than 3. To check that cutting out corners of length of about 1.31 maximizes instead of minimizes the volume, let's just check the sign of the second derivative of the volume function. Since it's negative, this means that the graph at that point is concave down. We know that we have found a maximum. From our piece of cardboard, we can cut off square corners of length 1.31 inches and fold up the sides, and this will construct the largest box possible. And you'll be able to give your professor the most jelly beans possible from using a 6-inch by 14-inch sheet of cardboard. Watch the 2 instructional videos to learn how to solve more optimization problems, because that really is what would make the instructor happy.